Okay, we left off last time with this beautiful picture here. Now, give me some feedback, actually. Did you guys totally blank out at this point? Or do you guys follow? Somebody did.
I did. I blanked out.
Yeah,
I
okay.
would like
I
to
don't
do
know.
this again.
I honestly cannot answer any questions on this stuff right now.
Okay, good. So then we'll do it again. But this is actually a very beautiful thing, if you understand. Well, actually, you know what I want to do? First, you know what? Let's go back to a different set of slides. And let's see if I can find it quickly. Maybe it's here. This is when we discuss single cycle. And I just want to, I think it's, yeah, there we go. Oh, I found it. That is satisfying to not have to look through 300 slides, but to find it quickly. This, what was this? Can somebody tell me what this is? This is back from chapter 4.
Controller?
Yes.
It's taking the opcode and deciding what op lines to
Right.
activate.
First of all, it says MIPS controller here, so it's a pretty easy question. But yes, these op5 and op0, those are the 6 bits of the opcode. They're going into this AND gate, and there's knots on it. Here, there's no knot. Here, there is a knot. And based on these results of these, the actual opcode is this is an amazing concept. You just thought it's like random numbers, the opcodes for this is 43 is, addition, whatever. You just thought it's just these random numbers. But it's not. It's in order to light up certain bits so that these AND gates will produce certain signals so that these or this not or this irregular line will produce the right zeros and ones for that command. So in a sense, the opcode is telling me, it's not just saying add, it's saying, we could rename it from add to light up this one, don't light up this one, light up this one, don't, that's what it is. That's what that command does. It does this, and it always will do that as long as this is the structure that we got. Does everyone understand my point? My point is that the opcode through these logic gates is determining what the controller will do. Anybody have a question about that? Now, what if I want to do something different in a different cycle? Can I do that based on this diagram?
What do you mean by something different?
In other words, on cycle 1, I want to have this be be 0. But on cycle 2, I want it to be 1.
Well, every other cycle, because it's single cycle, the opcode's going to change.
Say it again.
It's single cycle, so every cycle, every new cycle, the opcode will change, should be different.
Yes. So my question is really not. So I'll refine my question. My question is, could I use this same structure for a multi-cycle version of MIPS?
You need a state machine to keep track of what has come in the past and flip-flops and stuff.
Right. Well, that's exactly the point. Right. The answer is no. Does anybody not see why this will not work in a multi-cycle? Does anyone not see why this cannot work in a multi-cycle, or this is insufficient for a multi-cycle version of MIPS? Don't be afraid if you don't understand. I'm happy to explain it again. Okay, so I assume you understand that. And I'll just say it in my words. The basic reason is because this only does one thing per opcode. If the opcode is add, then that's all it does. It can't do anything else. It's fixed. There's no way to change what it does. There's no way to change what it does. It's dependent entirely on one thing and one thing alone, the opcode. So that is what you had done. So therefore, this implementation cannot work in a multi-cycle version. So actually what we're doing now in chapter 12 is explaining how to write the same thing for a multi-cycle computer. So that's what this diagram, this beautiful diagram is. What it's saying is like this. Wait a second.
So when we're talking about the controller being a state machine, serial state machine, we're talking about the controller in a multi-cycle. We're not talking about single cycle.
Yeah, single cycle doesn't make sense to be talking about. It just doesn't, is incongruous. If it's single cycle, then there are no states because everything happens in one cycle.
Right.
So where's the state machine in this picture?
Well, essentially well, let's explain the picture. First of all, you got a clock coming in here. And as we saw before, when you have a count register, or what is it called? Shift register. No, count, what do we call it? A count register or a shift register? Counter. Call it a counter. A 16 bits, whatever, 16 synchronous up counter. Up counter because it goes up. Okay, so we have a counter every clock cycle, assuming that the PE is disabled and that we haven't done a clear over here, and that the chip enable, that the count enable is set to 1, it's enabled. Assuming all that, then every time there's a clock cycle, the Qs are going to go 0, 1, 2, 3, up to 16, and then back to 0, 1, 2, up to 16. So we have essentially as many as 16 states because these values have 16 different options. All zeros or 0 and then 3 ones, you know, all these 16 options. So there's 16 states. And basically what we're saying here is this, with the help of this ROM, we can say if it's state 0, then the ROM just means memory. So we can think of this number as actually the line, the address in memory for a certain piece of data.
Meaning, so like what a cycle does is stored in memory?
Exactly. So what I have is that this I have a picture of it. Not really, no.
So this is like a sort of backup program, so to say?
It's like a little program. It's like a little program. It's 16 lines of program because there's 16 different options here, 16 different addresses. And if I'm on line 0, then the data stored in address space 0 will come out on these lines, however many lines these are, these M lines. And we call them the tune. That's the data. The data at that address. This is the address. In other words, you can think of the state as an address in the ROM. That's the jump.
So this outputs the data from that address?
Exactly. This is a ROM. That's what ROM does. You give it an address, it gives you the data at that address. That's all a ROM ever does. That's what memory does. ROM is the same as RAM, you know, as far as we're concerned.
So this is a read function, not a write.
Well, ROM is read only. So yes, this is for sure read. We're only read. It's read only memory. This is memory that we can only read from. That's why there's no write enable or read enable or anything. It's just a read only memory. So we put in address 0, and whatever's in line 0 in this ROM will come out. Whatever in line 1 will come out if we put in 1 here. If we put in 15 here, we'll get the last line of data will come out on these lines. Now, what is the meaning of these lines? They have some meaning. Well, we're going to divide them up. We're going to say some of them have one meaning, and some of the bits that come out have one meaning, and some have a different meaning. So what we're going to say is like this. Remember when that picture that I showed you from chapter 4, where we saw the controller lines, the output lines of the controller? Well, that's what these number of bits are. Notice it's not a fixed amount. It's whatever the hardware designer designed. He could make it be, this could be a 32-bit data. This could be a 64-bit data. Who knows? It could be anything. It could be 128-bit data. whatever number of control lines I need is this amount of the, let's say it's 16-bit data, and I need 8 control lines. So this is 8 control lines. And those are the actual control lines that if it's stage 0, do these control lines. Stage 1, it'll print out different data and it'll do these. These will be the control lines. So what do I need this for? This, yeah.
Okay, go on to the next instruction.
No, it automatically will go on to the next instruction. Because of the counter, every clock cycle goes up to 1. Now it'll put out new, if I have a simple thing where my computer, all it does is 16 different things, it has 16 stages, and it always does the same 16 stages, then I don't need, then I'm done. All I need is this and this. I don't need these bits at all.
I'm a little confused. Why do we need a counter that goes up to 16? For multi-cycle, aren't we only dealing with 5 cycles?
Because we're not talking about MIPS. We're talking about any theoretical computer.
Okay.
Wait, so the memory can only understand certain cycles, meaning different cycles are going to be different for different opcodes. So how does the memory know which one it's?
That's exactly, we're going to get there, but let's go slowly. First of all, imagine a computer that has just 16 steps, and it always does the same. All it has is one opcode. Opcode is, do your thing, baby. And we just tell it, do your thing, and he goes through his 16 stages, and he prints out 16. Now let's say we have 2 things that it does. It does thing 1 and thing 2. Thing 2 is exactly like thing 1, except it skips step 14. It goes straight from 13 to 15. Can we do that? How can we do that? So what we can do is we can say like this. We want it to go from 13 to 15, right? So what we'll do is in address space 13, we'll keep our control lines just like they were. But in the link T space, which we also have in the data, which we've never used up to now, it was all zeros. Now we'll put in it the value 15. So that we'll have the next place to go and to skip 14, and we'll put the value 15 in these bits. These are 4 bits. We can put 15 in there. So we'll say go to 15. And those bits are going to come over here, and there'll be 15 over here. Now, normally, if it's a regular do your thing 1, then they'll go in here, but PE enable will not be enabled. So it'll be step 14, it'll be step 13, and PE will be not enabled. And even though there's 15 here, it'll still go to step 14 because I didn't write the 15 over here. But when it's thing number 2, and what's this? And it's step 13. In other words, I take these bits, which is, of course represent 13 now. And I take the 13 and I shove it into here. And I say, and this guy says, oh, it's step 13? Well, if it's thing number 2, I'm going to enable this so that the 15 will get written here, and he'll skip step 14 and it'll go straight to 15.
I'm getting a little confused. What do you mean by thing 1 and thing 2?
I said that let's say we have a computer that doesn't do just one thing, it does 2 things. That's what I mean by thing 1 and thing 2.
So only for thing 2 will it skip 14?
Exactly. And I'm explaining now how it's going to accomplish that amazing task. What it's going to do is it's going to be notified by these bits that we're on step 13. And it's going to say, oh, it's step 13. I better enable PE so that the 15 that's written over here gets put into the Ds so that they come out on the Qs next time instead of the normal 14. It'll be go straight to 15. Now, that will be great if I always want to do thing 2. But that, if I just put 13 here and he always, when it's 13, he puts enable over here, then I'll always skip 14. But that's not what I wanted. I wanted sometimes to do 14 and sometimes do 15. Sometimes this to be enabled and sometimes not. So it's true I can identify that I'm on stage 13 with these steps. But I need also to be able to know that I'm doing thing number 2. I'm doing activity number 2, whatever it is. It could be minus. The first one was add and the second one is subtract. So thing number 2, how will I know that I'm doing thing number 2? These lines here. These lines here are the opcode. If these lines here tell me that it's thing number 2, then when it's step 13 over here, I'm gonna boom, put out enable. And then he'll know to take the 15 that's written over here on the data in the address and put that into the D so that we go straight to 15 and skip 14. Isn't that amazing?
Is that opcode coming in from the control?
No, that opcode is going in from a command, the instruction. That's the opcode from the instruction. That's the 6 bits of the opcode.
But
Of your
there's 16
instruction.
bits here.
Again, this is a theoretical computer. I can have it only be 6 if I want. There's dots here. I mean, you're right. He did it.
It's 16.
It is
It's
6.
0 to 15.
What?
It's 0 to 15, it says.
Because
You just
you're
said-
saying because this is 16, this has to be
No,
16?
it says on it. 0,
I know
1,
it's
2,
16.
3, 4.
I know. Yes, you are correct. It is 16. I'm ignoring that. It doesn't matter to me.
Okay.
That's because this was written for a computer that has a 16-bit opcode. Okay? If it's a MIPS computer, it only has a 6-bit opcode.
So we're looking at that. It's 6 to 1.
I mean, it doesn't matter. It just means it doesn't matter. These are, what it says here in Hebrew is Tanaim libitzua kvitza. The conditions which will tell me whether or not to actually execute the jump that has been put in here. This is always a jump. This is saying go to skip 14 and go straight to 15. That's a jump. This jump address should or should it not be done? Well, this will be the conditions that will tell me that. That could be the opcode. In other words, if it's a subtract, then jump 14. If it's not, then, and furthermore, I just did for one. I can do for every single stage, I can give it another place to jump to. But guess what? This only works if in stage 3, I only have 2 options to go to, either left or right. Either the sequential one, in other words, if I'm on stage 3, I can only go to stage 4 or to one other stage. I can't go to 6 other stages if I'm in stage 4, right? Because I either go to the next incremental stage or whatever stage is written over here. And that's why it was so important to explain to you that we're going to use a diagram like this, where every stage has either continue or do something else. Never 2 possibilities, never something like this. Always the stage is binary, like this. Every stage has to be binary. Either continue, either go to alpha, which is, you know, if alpha is true, then go to stage, the next stage, x plus 1. If alpha is not true, then go to one other stage, not multiple other possibilities. And that we can, and that we needed to say in order to be able to implement this thing, which has only 2 options. Either do the next incremental one, which is whatever the queue would ordinarily give you, or override the queue by whatever is written in the data in the ROM in this section.
I have a question.
Yeah.
So this ROM that you're talking about, it's not like the actual memory of the computer itself. That's a separate
Yes.
memory. So why are we using a ROM here as opposed to something faster?
There's nothing faster than a ROM. You mean a register? I mean, you want to make it use? We could use registers.
Isn't a cache also faster than a ROM?
The real reason why a cache is smaller is faster is because it's smaller. This is extremely small, so this will be pretty fast.
Okay.
There really isn't anything faster than a ROM. ROM is very fast. Even a register, which is very fast, is probably slower. I mean, you know, this is all. Don't get hung up on that. When we say that ROM is slower than registers, it's mostly because it's bigger. But such a small ROM will be perhaps faster than a register, because a register has to have the ability to read and to write, whereas this ROM is just a writing, so it might be faster. Again, these are all technological issues which can change every 5 years, you know.
Okay.
Okay, so I just now explained the thing. So here's the explanation of the illustration. Each word in the ROM corresponds to a particular state in the state diagram. A modulo 16-bit counter is shown in the figure because the counter value is the address for the ROM, so the ROM will have 16 words. Okay. Right, using this ROM in the illustration, we determine the jump targets. Exactly, like I explained. Assuming the jumps conditions are met, as shown below, the jump target will be determined by the loading, by loading the counter with the value written in the linked T field. Oh, that's what I just explained. Okay.
Wait, so that's not 16 bits, that's 16 times 4 bits?
What? When you say that, I don't know what you mean.
The address in the address from the counter to the ROM.
The address from the counter to the ROM is 4 bits, which have 2 to the
Okay.
which have
Yeah.
2 to the 4th possibilities, which is 16, which is why he says it's a 16 16 words. The ROM will have 16 words. When he says words, he means we don't know what the word length is, whatever the word length is.
Okay, so this is not assuming the word is 4 bytes or whatever it usually is.
No, again, this is a theoretical computer of any size. If I needed 1,000 control lines, then there'd be 1,000 lines. Then it'd be much bigger. It would be 1,004. This kind of, the linked T, does have to be 4. That has to be 4. It can't be 5 or 3. I mean, well,
It has to be the
it
same
basically has
amount.
to be 4 because I have to put in data on all these 4 lines. So this has to be 4. So
So it has to be-
the minimum length of this would be, 5 bits. I mean, kind of absurd, but the minimum length would be 5.
But the linked T could be more if there was Q0, Q1, Q2, Q3, Q4, right? Or something like that.
Yeah, exactly. If my counter had one more bit, then I would have a 32-bit counter. I would be able to count up to 32, and I would have to have one more bit of data. And it would give me more stages. It would give me the possibility of having 32 states in my computer. But let's keep it to 16. Okay. The contents of the word in the ROM can be divided into 2 fields. The 4-bit link field is the field that specifies the next state when the jump condition is met. This should all now make sense. If I had read this to you before, it would have been confusing, I think. Next state code when the jump condition is met. And then there will be a parallel loading of this value to the counter. Right, if I want to go to a different stage, I'll have to parallel load whatever is in the linked T field. If the jump conditions are not met, then there's no parallel load, and instead the counter will advance to the next sequential state. As we said, control field. So that's the other part of what's the values in the address space.
So one cycle can only jump to one other.
Exactly, that's what I was explaining. That's why we had to create a diagram where every state had either 2 alternatives, only 2 alternatives, no 3 alternative states. That's why we simplified this to this. This state has 1, 2, 3, 4 possible places it can go. That's no good. We couldn't possibly implement that with our ROM. We could implement it with logic gates, but we can't implement it with the system we came up with. So we're going to change it, and we're going to add more states. And each state will be a binary state, which we need to have to do our ROM. Each bit in this field indicates one output of the controller. So the number of bits in a field is the same as the number of different outputs of the controller. Right. So the function of the ROM is, when given an address that is actually the current state, the controller outputs for that the control outputs for that state appear on the control field of the output word in the control field. Right, that's what we explained. The linked T field will have the state of for the jump to state, wherever I'm supposed to jump to, if the jump to condition is met. Then it will jump to that state written in the linked T by loading this value into the counter, as we explained. If the conditions are met, then this value will go into here, and I'll jump to that address over here. If the condition is not met, then obviously we will ignore the linked field. Important. To entrance II, or one, I don't know, II of the multiplexer, we will connect the jump condition in state I. So he's explaining a little bit different from what I said. He's saying that, basically what he's saying is like this. Right. I was saying that this is directly the opcode, which it could be. It could be directly the opcode. But it could also be conditions. It could also be if, you know, the subtraction, you know, it's a branch. And if the subtraction produces 0, then that, you know, if that's true, then jump. Otherwise, don't jump. So I would essentially put the subtraction and the result of the 0 line, I would put it, you know, on I0, on input 0. Input 0 would be that if I'm in stage 0, and well, it's impossible kind of, but let's say stage 1, and I'm in stage 1, and I did a subtraction, and I got 0, then I'll have a 1 lit up here, and it'll indicate to this guy, if this is, since this is stage 1, then jump to the location. You understand what I'm saying? In other words, I'll have a different condition attached to each one of these lines, and that will be the condition that I will check if I'm in stage X, stage I. For stage 2, I'll have the condition line. Notice this is a line coming in from the data path. Everything that's not the controller. Whatever. The point is, I have some conditions over here. Doesn't matter whether it's the opcode or not, or some other. You know, opcode is like not a condition. I mean, it is a condition, but it's not something that's unknown at the beginning. We know it. We know the opcode. We can have all the bits of the opcode, and the opcode could be, you know, in stage. The opcode will tell us that in stage, you know, 2, light up this light. Yes, I want to jump to the condition because it's this particular opcode. Or the condition could be because of some procedure that we did in data. Fine. The state diagram based on the new ASM and suited to the controller using a counter and a ROM. Note, we could have gone directly from the first state diagram to a state diagram where each state has just one condition to check. In other words, what he's saying is like this. We started off with, the buttons are very close together, and even that's the problem. See, this is not a good diagram because it's not binary. I can go right or left, and I have different reasons why I might go right and left. It's not a binary diagram. So in order to turn this into a binary diagram, we did a roundabout kind of procedure. First, we turned it into, well, we went back to this thing. We had originally gotten that thing. We went back to this thing, and we turned that into binary. Then once we put that into binary, notice we have 1, 2, 3, notice there's numbers here, 3, 2, stage 0, 1, 2, 3, 4, 5, 6. Now we turned it into binary states. And now that we got the binary states, we're going to go back and create this thing, which has got 6 or 7 binary states. That's essentially exactly what we just had before. What lines to output in state 1, what lines to output in state 2. State 3 is not, we don't line output do anything. State 4, we don't do anything because those are just filler in states that we can test these other things. And we have 6 states now. And now we can actually draw the full diagram for this particular computer. I see I've done it all here in words, but let's look at it ourselves before we look at the explanation. So you see he's not dealing with, there's no I mean, in this diagram, there are no opcodes. That's why, and I was trying to compare it to what we did before. But look here, we have start. So what it says is, in state 0, if the start line is activated, then jump to the next state. Let's go to the explanation. Wait. Maybe I explain it better over here. In the state diagram, there are 7 states. Therefore, we can implement the controller with a modulo 8 counter. In other words, we need at least 7, so we'll use an 8 because there is no such thing as a 7 counter. In analysis of state 0, the system starts after receiving a clear, inverted clear equals 0. That will reset the counter ports, which are the state code. This means that the controller is now in state 0. The controller outputs are passed as a ROM address. So the ROM address 0 is now accessed. The state to which we jump, if start is equal to 1, is state 0. So the link bit address are 0. So here, so look here. Notice the zeros here. Notice that we only have 3 bits because it's not 16 now, it's 8. He used the same diagram and he just put a 0 here. But notice 0, 1, 2, 3. So those come in here and they go up to here and they tell us where to jump to. And it says jump to where? To 0. Well, that's actually a jump because if you think about it, the next state after state 0 would be state 1. So we're telling it, don't go to state 1. If you're going to go to state 1, then this will have to be disabled. In other words, the normal thing that this counter does if it's at state 0, all right, let's start slowly. It's at state 0. What's it going to do? It's going to light up these control bits according to what's written for state 0. This little diagram here is the 8 rows of data in the ROM. Instead of drawing it on the same box, he drew it down here. So this is the ROM. And what comes out of these lines is 1, 0, 1, 0, 1, 0. Why? Ready is 1. Oh, to indicate that he is ready. Well, that's what we saw. If we go all the way back to the first one. In ready, in idle, it's supposed to ready bit is supposed to be lit. So that makes sense. And DRS 1 is 0 because we don't want to do anything with that. Why is the next one 1? Why is control reset, invert reset, whatever this is? Why is that 1? We saw that everything else should be 0. Why is it 1?
What's the DRS1?
I have no idea what it is, but doesn't matter. It's this thing. This is the DRS1. This is the DRS0. This is the control reset. Whatever they are, this is some theoretical computer. I don't care what it actually does. It counts the number of hairs on the moon. I don't know. I don't know what it does. But it has these lines, and I got to implement. In other words, I'm working like an idiot. I just take a diagram, and I want to build a computer according to that diagram because the master designer gave me this diagram, and I don't know what he wants. He wants some kind of computer that does this, and I say, okay, I'm not, without understanding it, I'm just going to read your diagram, and I'm going to build you the computer that you asked for. So I don't know what DR, what it stands for, and I don't care, but I do know that in this stage, this one has to be active, this one has to be active, this one has to be active, this one has to be active. In this one, only ready is active. And I'm trying to implement this state, which by the way is the same. I could look at it over here. Also here, only ready is active. Only ready is active. See, here I got a lot of things active. Here, only ready. And if I look in the final diagram, well, I also see the same thing. Ready is active in state 0. State 0, ready should be lit. State 1, I got a lot of things to be lit. But state 0, only ready. So my question to you is, why is there a 1 over here on this line and not on this line? And there's also a 1 over here on line 7, which is the invert set. Why are those two 1s? Shouldn't they all be 0?
Wait, is
Yeah,
that
they're
line
both
control
invert.
reset or inverse reset?
That line is called inverse reset. Inverse set.
If they're both inverted, then by putting 1s, we're really putting 0s there, no?
Exactly. Because that's the key word. I called them inactive. I said they're not they're active or inactive. That's the word we use. And these are active low. So therefore, I have to put a 1 here to make it inactive. So now we understand why there are these 1s and 0s here. That is the output that is supposed to be when I'm in state 0, which means the only thing that should be lit is the ready, and that is what's lit. That's exactly what I'm saying here. But, and normally after 0, I would go straight to 1. That's what this counter will do. It'll next take me to state 1. It'll, the values here will go up 1, and I'll print out, boom, I'll print out the next line. But sometimes I'm not going to go to state 1. I might sometimes jump to a different location. Where will I jump to sometimes? Let's look at the diagram.
0.
Back to myself. I'll jump back to myself. That's what that means. So I put in the jump location 0. And that will be the values that go into D. But those D's will be ignored most, unless something happens. Unless what happens? Unless what? Tell me.
The start
Unless the start is lit.
is not lit because there's a line.
Oh, because there's a line. Unless the start is not lit. So if the start is 1, then, right, so if the start is 0, then that means yes, start. I got to start implement as start indicator. Do start. So I'm going to enable the parallel load, and it's going to, sorry, getting myself confused. The normal thing to do is, sorry, if I don't have a start command, then this will be enabled. If I get a, what do I need? A 0 on this line?
Yeah,
So
0.
0 means no, a 1. Look, if I get a 1,
Then you go to the next stage.
then I go to the next stage. So that means if I get a 0, I do the jump. So that means if I got a 0 here, I want to do the jump. No, I keep getting confused. If I got a 0 here, I want to do the jump. Exactly. I want to go to the jump, which means stay where I am. If I got a 0 here. So therefore, I got to invert, but this hardware doesn't work by 0s. It works by 1s. So that's why I've got to invert the start.
It's inverted 3 times. The start's a 0, so then it gets inverted, and then it's a PE line.
No. Oh, well, here it gets inverted, but that's something else. No, but no, the point is, right, I've got to get, if I've got a 1, then I don't want to do this. So if I got a 0, I do want to do this. So I've got to invert the start so that when Kilo, I got a 1, then I want to stay where I am. But really, it's a 0. And we did all that just because we want it to make sense. We want 0 to mean stay where you are and 1 to mean go. But since I need a 1 here, logically means to stay where you are, I need to invert it. In other words, it makes sense for the outside observer that start equals 1 means you start. But if start would equal 1, then I would logically jump and I would stay where I am. So I got to invert it because that's the way this thing is built to work. So now we understand why this is start inverted here.
But why isn't it dependent on the rest of the I bits?
Because we're in state 0. All the S's are 0.
Oh, okay, bye.
Exactly. Very nice. In other words, because we're in state 0, these lines tell us only allow the bit, then this bit to come in. When we're in state 1, we're only going to look at this bit. You see how you could do this with an opcode, because I could have an opcode that the ones and the zeros, that the opcode is 1 0 1 1 0 1, you know what I mean? And then that would tell me when to do jumps and when not to do jumps, and that would be the opcode. You see what I'm saying? The opcode, instead of just being a random number, it actually is a set of ones and zeros which correspond to these input lines, which tell me in which state I'm going to need to jump, and that will be the opcode for that command. But here we're doing it. In other words, here we're doing it in a more well, whatever. We're not doing it with opcodes, but it could be done with opcodes. Fine. What about stage 1? Why are there all X's here in stage 1?
You don't care if there's no jump.
Because there's no jump. How do you know there's no jump? You look at the picture and you see here. No, if I'm in stage 1, I must go to stage 2. So therefore, I'm always going to jump. Therefore, there's a 0 hard-coded here. Never jump if I'm in stage 1. And this will be the output line.
What do we actually put in, like, how do we write that in terms of zeros and ones?
No, it doesn't matter. You can put all ones here. You can put all ones here, and the 0 here is going to ignore it. You see? Don't care means I really don't care. Put whatever you want. Put zeros and ones there. You can put
Where
ones.
did the outlines come
No
out of
matter
this?
what you put here, it'll work. That's the point. It's true. You're right. You cannot put an X there, but whatever you do put there, it'll work.
Where did the outlines come out of this?
Where do the what lines?
Like the upline, like the lines that control all the
operations here.
Yeah.
These ones here. I see it coming out right here.
Oh, this is just instead of like
Go to the data path.
the ALU source and whatever. This is instead of that.
These are the controllers. These are the output. These are the control lines that the controller must light up so the data path will work. Those are the lines that we see over here. Those are these DRS, these lines. Whatever's written underneath the line.
Okay, so
here,
like for MIPS, it's instead of like in MIPS, it would be like ALU source and whatever, like those.
Exactly. Yes. In MIPS, it would be ALU source. It would be reg to mem. It would, whatever those things are, that would be the values here. So stage 1, we understand. Yeah, go ahead.
How do we actually build it in a way that we don't care what? Oh, we just okay. I got it.
You could put as the designer, you can put whatever you want there. You can put all zeros there. You can put all ones. You could put 1 0 1 because you like that combination. Doesn't matter what you put there.
Basically, it's 0 on the input to jump.
Because whatever address I put here to jump to, since it's a 0 here, I'm never going to jump there anyway. So who cares what I put there? See what I'm saying? It doesn't affect anything. It has no effect. What about this 0 0 0? Why is it 0 0 here? I'm assuming you guys understand these ones, and I'm not going to explain them because it's obvious. Like they're whatever the lines, they're whatever the chart told me, whatever this particular picture told me. But why is it 0 0 on stage 2? Here was don't care.
Active.
What?
Wait, 0 0 where? Which?
In this one, this is stage 2, and this is the diagram. we wrote 0, 0, 0 for the place to jump to. Why is that?
Because that's the alternate
Because you go to start.
Because that's
option
where
as
he jumps
opposed
to.
to going forward.
That's the other alternative of the binary jump. And it's either he goes to the next one or he goes to there. That is his jump. So what should be written here for the next one? The next one is either go to the next one or the other binary option is to jump to stage 6. So what should be written here for stage 3? What should his be? What should it be? I'm going now the other way around. If I look at this and I say, oh, stage 3, he's going to 6. So what must be the jump location? 6. And sure enough, I go over here and I see stage 3, 4 and 2 is 6. Why is there 6 and 4? Let's see if that makes sense. 4 also goes to 6. Oh, that makes sense. And 5, what about 5? What should 5 be? Where is he jumping to?
It should be don't care because it's just goes straight to the counter.
Exactly. So let's see, 5 is don't care. And we got to better make sure that on 5, there's a 0 over there. Wait, why is there an end over here? On stage 2, let's go back to the chart. Because in stage 2, when do I make my jump? When the end line is lit. So I'm going to connect the end line up to this place. And we see now why we want it to be binary. We only want one condition to tell us what to do because it's going to be connected to this line. And that's what we have. We always have one, each line, each arc here has exactly one condition on it. That's perfect. Isn't that amazing? Now, this is all the explanation. It's going to be tedious to go through it, but we just went through it. So I'm not going to go through it with you. You can look at it if you want, but important to entrance I of the multiplexer, we will connect the jump condition in state I. Well, that's what we've been saying that all along. For example, in state 3, we jump when invert is true, invert equals 1, and therefore we connect condition invert to I3. Okay, we understood that. That's a major topic. Okay. I mean, we're kind of done with understanding how the controller works. Kind of. We understand it now. Or at least one way to do it. Obviously, we could do it different ways. We could make it with logic gates. Now, this is a bit of overkill if you think about it, because we're throwing at the problem this big ROM with all these, we're storing all these bits. And as we didn't try to build it with logic gates, we just threw a ROM at it. And we threw a multiplexer. You know what I mean? We threw these instruments to make our lives easier. But that's okay. Rather than build everything from scratch, it's better. Okay, designing the data path. Up to now, we talked about the controller. Like I said, we basically finished the controller. Now, what are the data paths? This is even harder, actually. How do you design a data path? Requirements. It must be flexible, that is, able to do different calculations. It must be fast. It's flexible. What do I mean able to do different calculations? It can't be that it just is one thing. The data path is what's going to, do processing on my data. It's going to do addition, subtract. If it just does one thing, it's not very useful. So it must be flexible. It can do different calculations. It must be fast and it must be cheap. Of course, we cannot maximize all of these requirements simultaneously. We can try to get a good compromise. Example, we want a machine, a logic circuit, to find, as a machine, like a processor, to find the sum of series. Stop. This is just an example. This is a simple, we're giving you, a problem. Okay. let's say you wanted to determine if it's a series. Given the set of numerical inputs, 0, 0. Okay, so we're saying like this. First of all, it always starts at 0. Then it gives us n, which is going to be the number of elements, I believe. And then it's going to give you the first element, and the second element, and then they give you the nth element. Then again, it's going to give you an m, and then the next element, the next element. And if it gives you, only when it gives you 0, 0, does it tell you that's a new list, that it's stopping to give you lists, essentially. Because it could give you M, I think theoretically it should give you also M, N, M, O. It should give you O and P and Q. It could theoretically go on forever. Because, in other words, once I've reached the nth letter, I'm either going to get here 0, 0, or I'm going to get another number like 7. And that tells me the next 7 numbers are part of the list. And then again, I finish the 7, I'll get either 0, 0, which I've done, or I'm going to get another number like 2, and it'll tell me the next 2 numbers are part of this. So it's going to just find the sum of the series. Very simple. Just want the sum. So you draw that like this. N, for I starts at 1. That's at this 1 here. Take the sum of x up to 1, each of them, until you get to n. That's just a mathematical way of writing what I explained. Notice that before each series, we are given the total number of elements in the series. Fine. Steps in designing. Come on. Plan the data path using standard components. Like a summer means like, so think it takes a sum, a register, a counter, which work on basic word sizes. Define the line of communication between the data path and the controller. In other words, make sure you have control lines and status lines from the data path. And then you have to do the actual design. So let's see. Basic components for a simple data path. Well, we're going to need a counter. Yeah, this data path is going to be a little different from the MIPS one, because it's going to be kind of like a, I don't know. Well, it's going to be specific to what our particular job is. It's built, we have a counter which is built from flip-flops. Features, what does it have in it, this counter? This is, again, off-the-shelf counter. Parallel loading, when the load equals 1 and the clock rises, then k bits from D enter the counter.
Why is it called parallel loading?
Yeah, because the k bits, it's not 1 bit at a time. We're loading all k bits. It could be like k could be 100. We could put 100 bits into the counter at once. Clock cycle, boom, k bits come in, and they're in the counter. This is the same counter that we saw before, except instead of saying it's a 16-bit up counter, we're just calling it a k-bit counter, and we're not saying if it's up or down. When the load equals 0, then on every clock rise, the data increments or decrements, because it could be an up counter or a down counter. And it has a save state. In the absence of a clock pulse, the counter maintains the current state. Okay, fine. We don't have a save state control line here, by the way. In the other one, we had a save state, the save state control line, which meant even if the clock cycle comes, we'll still save the state. Whatever. Register, built from D flip-flops. Whatever, serves as memory. Features. It has parallel loading when enable equals 1. You have enable, and then k bits come in, boom, they're stored. And there's a clock pulse. K bits enter in D, enter at D, and appear at exit Q. Q is register contents. In other words, the Q is the contents when I want to read it. Saves data. When enable equals 0, or if there is no clock pulse, notice if I enable it and I write, and I leave the enable on, then the next clock pulse I'll get the new data. The next clock pulse, new data. But if I want it to really act as a saver, as a real register, then I got to turn it on for one clock pulse and then turn the enable off, and it'll stay there. Well, we knew all that. All right, we're going to have to stop soon. Just one more thing. Okay. So ALU. Well, we know about an ALU. It has K, and K come out. It could also have a overflow. It doesn't. This one doesn't have an overflow bit, but it could. Based on the value of the control input, we also have an ALU function here, which tells it, are you doing add, subtract, shift right, shift left? and the result of the action appears in k bits online. For example, result could equal a plus b, or result could equal just a. By the way, that's also important. It could be that the function of this ALU will be just pass a through. Add 0 to a. Ignore b. I could theoretically, a function here could be ignore b, just pass a through. That's important. I will stop here and we'll continue next time.
Thank you.
Can I ask something small?
Yeah.
I see that our test is the 23rd, which is a pretty long time from now. Is it possible to do like a refresh lecture, or that we go over a test one of the days beforehand?
Yes, it's possible.